He's to talk with us about wood and air quality, how the technology addresses the issue. And John is a principal consultant in charge of air quality and permitting at Resource Systems Group in White River Junction, Vermont. And he's developed expertise in permit application preparation, air quality modeling, and best available control technology assessments through nearly 15 years of experience with biomass projects. And I will say that the speaker that we originally had tried, was going to come and fill this spot, couldn't make it at the last minute, and John graciously responded to a phone call on Friday and made time in his schedule to come down here and talk with us. So thanks a lot.
Sure thing.
You want to use the wireless?
No, I think just the pointer. Make sure I know how to. Can everybody? No, I don't think this is.
That's just for recording. That's
okay. Gotcha. All right. Well, good afternoon, everyone. We're still in post-lunch mode here. I have what I call a post-lunch food coma from about 1 to 3 p.m. when I'm basically worthless. So I'm going to do my very best to keep everyone here entertained. So yeah, my name is John Hinckley, actually John Hinckley Jr., and no, I'm not the guy who shot the president a long time ago, and no, I'm not related to him either, but I did grow up in Richmond, Virginia, 90 miles south of D.C., and we did get a lot of phone calls from like CIA and FBI and people prank calling and saying, hi, can I speak to the assassin, and things like that. So I don't care. You can make fun of me all you want. So I'm not that guy, but I am the guy that I hope you might call if you do need any form of air permitting. I help clients figure out how to comply with air pollution regulations, essentially complying with the Clean Air Act. So we do a lot of emissions estimation, air quality modeling of what happens with the emissions, and figuring how tall the stack needs to be and how much emission control you need. And we do some other things too as well. So I'm that, and at the end of the day, I'm Jack and Eleanor's dad and Leah's husband. So I'm just another person here. So let's talk a little bit more. But let me just back up here. I think the gist of this talk is just to really let you know what's happening in the Northeast and kind of how the community of folks involved in biomass energy in the Northeast have kind of rallied and really worked hard together to improve the state of the art and state of the practice with respect to biomass, getting over wrong impressions of biomass and helping kind of educate the public and helping figure out how to make it more efficient and cleaner and so on. All right, so obviously I'll need to give a little background, and then hopefully I won't put everyone to sleep with a little bit of talk about the EPA boiler MACT rule, aka the area source rule. And then hopefully I'll be able to keep you awake through some talk about permitting and emission thresholds. Those are important things to think about when you need to go through a regulatory agency to get a permit. Talk a little bit about what I call best management practices, or BMPs. EPA calls them work practice standards. They're kind of common sense things you can do to increase efficiency and reduce emissions, long story short. And then I think it'd be, sorry about that. And I think it'd be good to spend a little time talking about emission data. 10 or 15 years ago, we didn't have a lot of stack emissions data, stack test reports that were actual physical measurements of what the emissions are. And we have a lot of that data now, which is a big benefit, a big asset, I think, especially to this region. There's quite a bit of good data that you can hearken to. And I want to talk about air quality modeling. A lot of this talk will be on sort of electrical, mechanical, structural technology things we've done to kind of rise to the occasion. And I don't want to overlook computer technology, specifically computer modeling of what happens to the emissions, because I think it's really important to do that kind of modeling to kind of inform the design of the project so that you're not just designing a stack that should be tall enough. You want to design a stack that conforms with the national ambient air quality standards. And last but not least, I'll give a few parting thoughts if you're still awake. Okay, so more background, just a few pictures on, I'm going to get this clicker right here eventually. This is just an old school boiler, Massachusetts project I worked on. This is somewhere around 1950s, about a 30% thermal efficiency, no automated controls, but it's, that's one that's being phased out, and it's kind of the kind of system that I think a lot of people have in their mind, that the folks that might oppose the advance of biomass might kind of have something like this in mind. Although it's a great old furnace, and it does keep the building nice and warm, and you can probably also roast marshmallows next to it. So this is an example of an outdoor wood boiler, which is older, I'm assuming, and not terribly efficient, and probably maybe just starting up and probably burning old, chunky, punky, wet wood and making a nice big brown steam plume with it. Someone down the road from me has one of these, and he's saving a lot of money, but I kind of wonder at what point is he going to get tired of how bad his house smells as a result of it. But outdoor wood boilers have come quite a way, and there are newer designs now which are much more efficient and much more clean burning. The purpose of this picture is just to kind of illustrate the idea or the image that I think appears in a lot of people's minds when you start talking about developing a biomass project in their community. All right, so a little more background. Hopefully not too confusing slide here, but I could talk for an hour on the emissions from wood boilers, just comparing them with oil and gas and coal and so on and so forth. So this slide is really only going to scratch the surface, but the intent of the slide is really to show a couple of things. One is that wood is, generally speaking, on par with heating oil in terms of emissions. So it's not more, it's on par. It's certainly more than gas. And while not shown up here, wood certainly has less emissions than coal. Couple things here. What I want to show here, let's see, so wood is in blue, oil is in red, green is gas, and across the old horizontal axis here we have nitrogen oxides. They are a health pollutant, and they are an ozone precursor. That's why we care about those. SO2, sulfur dioxide, precursor for acid rain, and also impacts human health, so that's why we care about that. Carbon monoxide, or CO, that's a human health pollutant. We care about that. Particulate matter, or PM, is the buzz pollutant with biomass. That's really what we wind up talking about when we're in local hearings and so on and so forth, how there's usually a lot of discussion about how the fine particles will get deep into your lungs and cause adverse health impacts and so on and so forth. And we'll talk more about particulate matter and how we're controlling that pollutant. But this downward white arrow here is just to show you, roughly speaking, how much, in general, on average, particulate matter has been reduced over the last 15, 20 years. Again, these are just super ballpark numbers here. And I neglected to mention that what we have here on the y-axis are the emissions. And what I want to point out is the units of measure, because this is kind of the language that people in air permitting talk. The units are in the amount of pounds that are emitted that come out of the stack per million BTUs of heat input that go into the system. So pounds per million BTU of heat input is the language that we talk. And I think that's about all I really want to say on this. VOCs, volatile organic compounds, those are ozone precursors. That's why we care about those. And it's pretty much about the same for all pollutants. Last but not least, the hazardous air pollutants, or HAPs. Wood shows up a little bit higher in that category, but again, we're just talking ballpark numbers here. We care about HAPs because they can cause cancer and they can also cause short-term health impacts. All right, so we're going to talk about EPA boiler MACT rule. Everybody still awake? Raise your hand if you're asleep. Okay, so this, the boiler MACT rule, or the area source rule, comes from the Clean Air Act, and it comes from, was it Chapter 40, Part 63 of the Code of Federal Regulations, which is also called the National Emission Standards for Hazardous Air Pollutants. And what basically has happened is, over time, there was a lot of concern about wood smoke, wood emissions, particulate emissions, and there were a lot of groups that sort of formed and put the heat on EPA to revise this rule and put in it more stringent requirements on wood boiler emissions. And so EPA responded to that, and they proposed changes to the rule on, changes to the rule on June 4th, 2010. And one of the key changes was that all boilers were going to have to meet an emission limit of 0.03 pounds per million BTUs of heat input. That's a very strict standard. It applied to all boiler sizes. At the end of the day, the economy tanked, industry pushed back, everybody pushed back, and we wound up with a final rule which is a lot less stringent, a lot more flexible, and I'll talk more about that later, but that particulate limit I was telling you about was increased up to 0.07 pounds per million BTU. So it was effectively doubled, and it only applies to what we call large boilers, or boilers whose heat input is greater than 10 million BTU an hour. If you're having trouble going to sleep at night, go to the Federal Register and read up on the rule. This is just a summary of the rule facts. I'm not going to dive much into this. What I want to communicate is that the rule is kind of how the rule is structured. It's structured into existing units and new units. Existing ones are ones that had been constructed prior to 2010 when the rule changes were proposed, and new ones were those that were constructed after that. And it's divided into large boilers and small boilers. Large ones, again, are greater than 10 million heat input. Small boilers, less than 10 million. If you're less than 10 million, you don't have an emission limit that you have to meet. If you're greater than 10 million, you have an emission limit you have to meet, and you need to start thinking a little more intently about emission control technology, at least to meet federal requirements. One requirement for all boilers is a biennial tune-up. That's every 2 years. You have to do a tune-up according to EPA reference methods. And there's a lot of other record keeping and reporting and paperwork and so on that you have to do. So that's just scratching the surface on the boiler MACT rule or area source rule. Okay, permitting and emission thresholds. All right, so the purpose of this slide is to show you for each state in the Northeast what the threshold is for when you need to get an air permit. And what I think you'll quickly see here is that it changes. It varies on a state-by-state basis. And so what's really interesting, I think, is that in Vermont, if your system is about 6.5 million BTU an hour heat input, how do I say this? If you want to, Vermont it's 6.5 million, New Hampshire it's 2. The Connecticut River divides the two states. So if you want to build a 2 million heat input boiler over in Vermont, you don't need to talk to the Agency of Natural Resources. But if you want to build a 2 million BTU an hour boiler in New Hampshire, then you need to go speak with the New Hampshire DES. So it's there's a lot of variability in when you need to get a permit. What's in red here is, again, that 10 million BTU an hour threshold at which you become a large boiler in EPA's eyes, and at which you you are subject to an emission limit, and you're also subject to some other federal requirements, those being the new source performance standards. And I promise you I won't go into those. Okay, so this slide shows us even more variability, that being the variability on a state-by-state basis in the particulate matter emission limit. So just to recap a little bit, the federal government, or EPA, has its set of emission limits that you need to think about, and state governments have their own emission limits that you need to think about. So lots of complexity, not a whole lot of standardization, but at any rate, I just wanted to just kind of communicate this. What's interesting here, a lot of these emission limits are precedent driven. In other words, when you do a permit application for a new source, you have to do a best available control technology study, or BACT, in most states, not in all states. And the outcome of that study is basically, what do I need for an emission control device? And so as time progresses and more BACT studies are done, these emission limits on a state-by-state basis can change. So it can be a bit of a moving target in states that do BACT. New Hampshire, for example, is a state that is holding steady at 0.3 pounds per million BTU. They don't have a BACT requirement for small sources, and so that's been holding steady. They've been talking about reducing the limit to 0.2. Rhode Island is an example of one that has dropped from 0.2 down to 0.1 based on successive BACT studies. And over here in green, here's the EPA limit of 0.07 for large boilers. Again, that's those that are greater than 10 million BTU an hour heat input. So again, a lot of variability on a state-by-state basis. And for states where there is a BACT requirement, you can get a bit of a moving target on the emission limit. Okay, so now I want to talk a little bit about emission control technologies. And what I really want to focus on are what I call the end-of-pipe controls. Those are the ones that are located right before the stack. It's the last stop for the exhaust before it goes out the stack and up into the atmosphere. And I'm just going to focus on three kinds of control technologies, which are cyclone technology, fabric filtration, and electrostatic attraction. So cyclones, multicyclones, baghouses, and ESPs is what I'll be talking very briefly about. This is a picture of what's called a core separator. It's an example of cyclone technology. The idea here is that you're relying on the principle of centrifugal separation. The exhaust swirls around the cylinder. The particles hit the sides and then fall out and drop into a barrel. These technologies do work, and they are implemented still on an ongoing basis in the Northeast, and they're totally allowed in many states. They do have the lowest control efficiency generally, and they tend to be the least expensive. Some of them can be a little high on the energy side in that if you are running something with a high pressure drop, that means you need a big fan, which means you need a lot of electricity. So the electricity demand can run high in some of these. This is an example of an illustration of a fabric filter baghouse. The idea with this is that air comes in and is routed through these filter bags. The air goes through the weave of the bag, and the particles stick to the bag and accumulate there. And intermittently, air is shot through the bag to cause it to come off of the side of the bag, and it drops into a barrel below. And this kind of technology is super efficient. It can reduce up to like 99% of filterable particles. There have been some issues with them in New England. There's one I'm thinking about that did catch fire. They did remedy that by installing a cyclone in front of it to filter out any flying embers. So a little bit of a safety concern, but that can be mitigated. Highly efficient and moderately expensive. And last but not least, this is an illustration of electrostatic precipitator. Relies on the principle of electrostatic attraction. It's kind of like a magnet. Particles come in, they're charged, and then they're collected by plates that are oppositely charged. Those plates are intermittently wrapped or banged on. Particles drop out into a barrel. This technology tends to be the most expensive of the ones that I'm talking about, but lately we found ways, or people in the industry, not me, have found ways to design and build them less expensively. And the operating costs, the costs down the road, we're finding are lower, which makes them on an average per year basis less expensive than thought. The energy demand is a little bit lower than other technologies. They're thought to be a bit more safe, and they are slightly lower maintenance, especially lower maintenance than baghouses. I'm going to just talk a little bit more about ESPs, because what we've been finding in New England is that this is what. Okay, I'm good. I'm good. Hello. I think I'm all right. Let's try this for now. So over time, in the past 5 or so years in New England, a preference towards ESPs has developed. They are not the only thing that you can use in New England, but again, people are starting to go with them. This one is just in a corner of a room. They occupy a fairly small footprint. This one is on occupies a fairly small footprint, but it's up high a little bit. You might be able to see the collection barrels at the bottom here. And again, here's some more talk about ESPs. I said they're a little more economical than originally thought. They occupy a small footprint. They can also be installed outside, which is a plus. I believe I mentioned that there's less ancillary equipment, like insulated ductwork that goes with them. I was working on a project in Alaska, and we were originally going to go with a Baghouse, and the equipment vendor did some research and found that it would actually be, over the long haul, less expensive to go with an ESP, given, in part, one of the reasons was less ductwork to mess with. I think I mentioned they have relatively low power requirements, and they're low maintenance relative to a Baghouse. Baghouse, sometimes you need to shut down a couple times a year and do what's called blacklight testing, where you're putting a powder on the bags and shining a blacklight on them to see if there's any holes, and so that can be burdensome in some situations. Here's just a few pictures of systems that have ESPs. Up here's the Keene Middle School we did, which is the first permitted ESP in New Hampshire. And down here is the plant for the Weeks Medical Center in Lancaster, New Hampshire. That was the first ESP at a hospital in New Hampshire, I think. And one thing you'll notice is that there's no visible emissions whatsoever. If you stand outside, you're really not going to see anything. On a cold morning, you might see a steam plume coming out, but over time, as temperature rises and winds pick up, that plume will dissipate. Steam is just water vapor. It's not air pollution. All right, so best management practices are also called work practice standards by EPA. I like the term best management practices better, and I'd like to talk about those. The idea is, historically, we've focused a lot on the add-on emission controls. Do I need a Baghouse? Do I need an ESP? Will a cyclone work? And what I've really felt strongly about is that not enough emphasis has been on what can we do upstream to control emissions. So what can we do to improve combustion conditions? What can we do to improve fuel quality? Because what we're really doing is reducing the burden on the pollution control device. The less pollution you put into it, obviously the less that will come out of it, and the cleaner your system will be. I'll give some examples of them, but the gist is that they're really intended to increase your system's operating efficiency. The idea is that the more efficient your system is, the less fuel you'll burn and the less emissions you'll produce. And I have reviewed a number of stack tests that do suggest that implementing best management practices can reduce emissions. Reviewed a stack test for a facility that was using some pretty dirty fuel. It was basically a blowdown that had been ground up and had lots of rocks and dirt in it. And they brought it and burned it, and the emissions were about double what you would expect, but at least that fuel wasn't left to rot on the forest floor. Secondly, another example was I reviewed some stack test data that showed one facility, just by doing a tune-up, reduced their particulate emissions by about 60%. So stack testing sometimes can help reveal how efficiently your system is operating and kind of help you do some on-the-fly tuning up and help you figure out how you can minimize your emissions. Here's some examples. I talked about maximizing fuel quality. A fuel which is uniform in size and shape. Pellets are obviously kind of the epitome of that. Very, very consistent type of fuel. With respect to wood chips, if you have that kind of uniform size and shape, if you have minimal bark, minimal dirt, things like that, just doing whatever you can to maximize your fuel quality is a good first step. Having equipment sensors is a really good thing. Bill talked about the Okafen system, which has an oxygen sensor in it. The intent of that is to help maintain the proper air-to-fuel ratio at all times, and that's what keeps your system from smoking. And many systems have that now. Many systems did not have that years and years ago. Systems also have opacity meters and temperature sensors, and all of that is kind of feedback to the central controller of the system that helps it to manage the system and have it operate efficiently. Combustion efficiency testing is really not that big a deal. It involves using a portable analyzer and measuring the concentrations of CO and CO2, and you can plug those into a formula, and that will give you a sense for how thermally efficient your system is, and it's just a good way to kind of check on how your system's doing. Visual plume observations kind of means what it says and says what it means. It involves standing outside and observing the plume, and obviously if it's black and yucky, you got something to do to fix it. If it's invisible, then you know you're doing well. There are a few EPA reference methods that sort of lay out how you do this, so that there are some objective ways to go about doing this. So it's not just Joe Schmo standing outside. Gotcha, thanks. And we talked about regular tune-ups. I'm going to hit on emission data now. Where we're going to buzz through this. What we have here is the emissions in pounds per million BTU on the y-axis, and along here are the particulate matter, measured particulate matter in a stack test. And the abbreviation you see is a certain type of control technology that was at that particular site. So MC stands for multicyclone, FF stands for fabric filter, and then this green line here is that 0.07 pounds per million BTU limit for new large boilers. And what this really shows is that if you want to install a new large boiler, more likely than not, you're going to need some type of advanced emission control technology. In some cases, you would not need them. There are some systems that can be sub or be below 0.07 with a cyclone. Worked on a project in Massachusetts where we were able to justify, just by using pellets, that we'd at least be at 0.1. But generally speaking, for a lot of systems, you need to be thinking about maybe a Baghouse or an ESP or a really super efficient combustion technology or a really super clean fuel to get below 0.07. Modeling, this is just a computerized way to figure out where the emissions go. This little chart here is really exaggerated, but it's kind of like an industrial coal plant maybe next to a hospital. And what it's illustrating is when it's tall enough, it can kind of downwash on the leeward side of a building. And so the point of this graphic is that computer modeling of emissions can help you figure out how tall your stack should be to prevent this kind of a situation from occurring. I do a lot of work for schools, and they're very curious to know, will the stack's emissions impact the air intake or air handling units on the roof? And so we do modeling where we calculate the concentrations of various pollutants on the roof and make sure that they're within national ambient air quality standards. This is a picture of the National Life building that we did modeling for. This is the old oil boiler stack, and this is the new wood boiler stack. And I'm pretty excited because my stack, the plume's going higher, actually, than the old stack. So it just goes to show, putting some thought into the stack design can really help you loft whatever emissions are remaining up in the air. I mean, what we're looking at here is a steam plume, essentially. This was taken on a cold January morning. Here's an output of a little graphic I produced. It's probably not going to make a whole lot of sense, but it's the kind of thing that we can produce for our clients that basically tells them where the maximum concentrations will occur, how high will the concentrations be, and will they be within national ambient air quality standards. Just some parting thoughts. I really feel like the whole biomass industry has teamed up well with the public sector in the Northeast. We've had our squabbles, but I think we've all kind of worked hard together to find ways to improve the technology and ensure that environmental rules and regulations are met without breaking the bank. We talked a lot about how there's variability on a state-by-state basis with permitting thresholds and emission limits, and talked about how we need to think about best management practices in addition to add-on controls for controlling emissions, possibility of cyclone technology not meeting stricter emission limits in some cases with some kinds of technologies, and then wrapped up with just how air quality modeling can be a useful tool in helping inform your design, helping you figure out how tall the stack needs to be, how much emission control you need. So, and I wrote a report with an organization called Biomass Energy Resource Center called Emission Controls for Small Wood-Fired Boilers. If you're having trouble sleeping at night, you can download that. But it talks a lot about the stack test data that's available, costs of emission control technologies, and just talks a lot about what I just spoke about. And last but not least, here's the contact info. This is a view of Heartland, Vermont, where I'm from. If you call me and I don't answer, it's hopefully because I'm on this right here and enjoying riding the trails and watching, looking at Vermont's beautiful forests. So thanks so much. Appreciate you staying awake, sticking in there with this talk.
Time for some questions. John always has a question.
John, thank you. One of the things that I wonder if you'd touch on just a little bit is the difference on a hot water boiler system between operation at full load when there's a call for heat and what they typically will do when the heat load is met and that unit's just idling, what that does to your combustion, what that does to your emissions, and potentially what the value of a thermal accumulator could be in reducing that negative effect.
Sure. So I think, the gist of the question is, well, what's going on here is for a lot of biomass systems, let's just take one that heats a public school. When school lets out, I'll put it this way, early in the wee hours of the morning, the boiler will cut on to warm the building up. The building will be calling for heat. The boiler will rise to the occasion, turn on and rise up to what I call high fire, or maybe close to 100% load, full design capacity. And it's just making a lot of steam to produce heat for the building. And typically that's when a boiler runs most efficiently. But what happens is, obviously during the course of the day, it warms up and the building will call for less heat, and so that boiler will then revert to a lower operating load. And in many cases, a boiler which is operating at a lower load might not operate as efficiently as it did at the higher load. And so in many cases, what people are doing is designing boilers or undersizing them a little bit so that they'll run a little harder during the course of the operating cycle. And then, of course, the wood boiler, the technology vendor can also optimize the boiler so that it is as efficient as possible at all operating loads. And there's also the thinking that, or at least with smaller systems, having what's called thermal storage, which is basically like a big tank of water that will act as a thermal accumulator, so that when the buildings aren't calling for heat, the boiler can still run at a higher load and pump heat into this thermal accumulator per se and stay efficient. So that's my understanding of it. I haven't done the thermodynamics research on it or anything like that. But does that answer your question? Yeah.
Any other questions?
What is the life of a baghouse filter?
Good question. It really depends on how long the boiler is running during the course of a year. If it's just for thermal, the system's likely not running in the summer, which will then increase the life of the bags. We're thinking initially more like in New England, with an average New England thermal system, maybe once every 3 years, but I think what we're finding is that they do last much longer, maybe twice that amount. And I don't know the exact answer to that, but what I can say is what was originally anticipated seems to be being exceeded. And again, it's just a function of how hard and how long that boiler runs.
Well, thank you very much, John.
Thank you.